Welcome back to the Climate Action Stage. Hopefully you got a chance to watch the lightning talk that we played in the break. We'll be showing these in between sessions, and they'll each showcase an innovative piece of Turing Institute research in action. If you want to watch the videos in one or any session again, you can go to the on-demand section in Hopin. Now for our next session. We're talking specifically about climate and environmental change and how AI and data science can be utilised to mitigate its effects and ensure that we have data that we need to adapt to those changes. I'm pleased to introduce to you our host for the session, Professor Gavin Shaddick. Gavin is a chair of data science and statistics at the University of Exeter and co-director of the Joint Centre for Excellence in Environmental Intelligence, a joint research centre with the UK Met Office. He's director of the UK RI-funded Centre for Doctoral Training in Environmental Intelligence, Data Science and AI for Sustainable Futures, and is co-lead of the recently established theme in environment sustainability at the Alan Turing Institute, where he is a Turing Fellow. Over to you, Gavin.
Thank you, Shinny, and welcome everybody to the climate stage. It is my great pleasure to introduce three panelists today. Associate Professor Emma Bland from the European Centre for Environment and Human Health, Professor Marta Blangiardo from the Department of Epidemiology and Biostatistics at Imperial College, and Matt Fry, who is a manager of environmental informatics at the UK Centre for Ecology and Hydrology. Just a quick word about the format of this session. We're going to have some introductory presentations from our three panelists, after which we will turn to a question and answer session. And so if you have any questions for the panelists, either on their presentations or more generally about the use of AI and data science in addressing the problems associated with climate change and environmental change in general, then please enter those questions into the online platform, and we'll take those and present them to the speakers. So without further ado, I'll turn to Emma, who's going to give us a presentation on the Local Climate Adaptation Tool, or LCAT.
Thanks, Gavin. This morning I just wanted to give you a very brief introduction to a project that we're working on at the European Centre in partnership with our local authority, Cornwall Council, and local SME, Then Try This. The project is aiming at how do we support local decision makers that use evidence to inform their adaptation decisions. So just a little bit of history. Where we started was looking at how local adaptation decisions were being made locally, and what, if any, role the university could play in supporting those decision making. And we did that through a series of engagement activities, through workshops and sector and one-to-one meetings with members of our local council, Cornwall Council, our local NHS partners, our emergency services, and also representatives from the voluntary and private sectors. And what we found was that there was a real recognition that adaptation was required, but that there was very limited action actually taking place. There's a lack of financial and time resources, and also a lack of expertise and confidence about what decisions should be made and how to use evidence to inform that decision making. There was a clear desire to work across the traditional boundaries that exist in local authority decision making, and involving the wider organisations that reflect the local society, but also a need to focus on inequalities and a recognition that vulnerable members of the community are going to be more impacted by climate change. And what was quite interesting for us was that after a little while we actually started to realise that people didn't have a clear understanding of what the climate for the future of our area was going to be, and that there was no recognised climate model that was in place for the local area. So this led us to think about what the university response could be, and our stakeholders told us that they would like some help in working across their traditional boundaries, some access to the evidence base in a moderated and sort of curated way to help them make decisions more easily and more easily apply the evidence to their decision making. They wanted some sort of a place they could see good practice showcased, and they also wanted us to provide them with access to a local climate model. So our response to this was to develop LCAT, which is a local climate adaptation tool, which is a decision support tool that really helps people to have easy access to evidence that they can explore in whatever level or detail they would like, and some recognition and some sort of recommendations for action that can be taken. And to facilitate that cross-service approach, we were using health as a common language that people recognised and valued as an approach to use. So the local climate adaptation tool basically works by allowing the user to select the geographical area they're interested in, see what the climate model for that area is in whatever characteristics they're interested in, explore the health impacts of that change, and then see some recommendations for action. So the local climate adaptation tool, and hopefully this will work. So this is our prototype. The user can select the geographical area they're interested in. This is a map of Cornwall. See the climate graphs for Cornwall, identifying which characteristic they're interested in. So here it's temperature, and then go down to explore the impacts of that change. Now, hopefully this is bigger on your screen than it is on mine, but on the left-hand side, you'll see these are the main climate variables that will impact active travel, which was the model that we developed for this prototype. You can then click on the arrows to see the evidence base that has led to the map being created, and then the nodes identify particular issues that will be impacted by climate and have an impact on health. And any node that has a yellow ring around it will then expand out to other impacts. And as you click, you can build the model, and you'll see because this is a prototype, you'll see we still have a bit of work to do on how we present this information. But what this allows you to see is, if you're able to deal with it, the complexities of health impacts and climate change, and all the various reasons why people need to work across the current sort of traditional services and practices. So then the tool then takes you on to looking at adaptation suggestions, and again, they can see a basic proposal or recommendation, and then see the evidence that comes from that. The climate tool development now we're at the next stage of this project, which is to look to see the availability of local climate models at a national level. So what we want to do is expand the value of the tool nationally, but actually finding local climate models is one of the challenges that we've addressed. That we are addressing, and we're working with Turing Institute's DIME project to help us in support of that. We also want to widen our stakeholder engagement. Currently, we've engaged with our local decision makers, which is in the southwest of England, and we're now going to be expanding that, moving into working with Bristol, but then also taking that further. And then we also are looking at how do we develop and maintain the evidence base and the impact pathways, because clearly evidence is being accumulated all the time, and how do we maintain and keep up to date that element of the tool. We're also exploring the inequalities issue, which was clearly an important factor for our stakeholders, saying how do we identify the vulnerable communities that are most likely to be impacted, and how do we identify those within the tool without then making the tool too complicated and inaccessible for other users. And then generally looking at functionality of the tool. How do we bring in the case studies element? How do we improve the graphics? How do we show correlations and various other issues that we've been looking to address? So I just wanted to reflect on and thank our funders, who have included Research England's project support, Priority Support Fund and Strategic Priorities and Partnerships Fund, the LGA UCL Net Zero Programme, the Schroeder Foundation, and also to acknowledge now that we're working with the Turing Institute's DIME project in developing the next step for this tool. Thank you.
Thank you, Emma. That was great. I wonder if I could just follow up on the inequalities point. And I wondered if you could just give some more explanation about what kind of inequalities you might expect as our climate changes.
I think what we're seeing, and I'm sure that Marta has things to say on this as well, is that vulnerable communities more generally, and how you define those is one of the challenges, but vulnerable communities who maybe have low income, who have multiple health challenges already, sort of a range of comorbidities, are more likely to be susceptible to climate change. If you are in a low-income household, it is often the case that your home may exist in an area that is more susceptible to climate impacts. The very way that the home is built may be more susceptible. So there's a whole host of areas where, depending on that definition of vulnerability, climate will have a particularly great impact, and also that you're, as a householder, as a community, you have less resilience. So you have less options in how you address that.
Brilliant. And just before we move on to Marta, one of the things we might cover in our panel Q&A is whether the data is available and easily accessible to define vulnerable populations and their exposures, just a heads up. So now we'll turn to Marta Rangiardo from Imperial, who's going to give us a short presentation on air pollution sources, entitled Hunting for Air Pollution Sources.
Thank you, Gavin, for the invitation. I'm really happy to be here. So I'm kind of like move us a little bit, on a different direction, if we may, which is air pollution. And just to give you sort of like a brief background, obviously air pollution and climate change are very intertwined. We all know the greenhouse gases increase the temperature of the Earth. We also now know that PM, for instance, or particulate matter in very remote places like the Arctic, apparently casts shadows on the ice, and that increases the temperature. And also we know that smog, for instance, is worsened when there is increased heat. Air pollution is also featuring into the SDGs. So in the goal 3, which is related to improving the health of people, the SDG 7, which is related to cleaner energy, and 11, which is related to sort of like less impact of urban environment, so basically improving air quality itself. Now, obviously, air pollution has an impact on health, and we know now that since 2013, basically, outdoor air pollution has been defined as carcinogenic. There are around 7 million deaths every year, which are due to air pollution from the latest WHO report. And there is a synergistic effect between temperature and air pollution. This has been studied a lot, both related to general mortality, hospital admission, but also related to cause specifically cardiorespiratory health. Now, obviously, nothing is really easy. So air pollution is not easy to handle, particularly because if you think about it, when we breathe, we don't breathe one pollutant at a time, we breathe a mixture of things, right? If we focus on PM, and you see in that picture there, basically you would have the mass, the PM concentration, and you would have primary particles, which are the ones emitted, for instance, from exhaust of the cars, but also secondary particles, which are they're created in the atmosphere through precursory gases. So now the problem we face is that we don't really know the toxicity of the different sources, and that's what we need to try and study. Because obviously, if we really want to make a difference in terms of policy and target policies, we need to know which one to target, basically. So that's what source apportionment is about. And source apportionment is challenging. And basically, there are two things. One is, obviously, we have loads, as I said, of components or particle sizes, for instance, that we want to try and make sense of. And they're very correlated, as you can see in this sort of like plot. Now, I'm sure you all think about dimension reduction when I say high dimensionality and correlation, and this is exactly what people have been doing. Oh, my equations don't work. Anyway, there was supposed to be a factor analysis where you had the factor loadings and you have basically the source profile density. So there was a combination of source profiles and also the contribution of each source to the total particle. So basically, this is used a lot in environmental science. It's called positive matrix factorization. And what you have on the right in the plot is the output from it. So basically, the total concentration is split into different proportions. Some can be from the cars, some can be from industry, from biomass burning, and so on. The limitations are the general limitation in a cluster analysis, so you basically need to define the sources a priori. It's quite tricky to include uncertainty, you need to do some sort of bootstrapping, and then you can't really account for space and time dependence. So this really calls for something a little bit more flexible. And this is where machine learning, AI can really help. And in particular, I'm thinking about Bayesian non-parametric, which gives a high degree of flexibility. So basically, you have an infinite mixture of sources, which is approximated by something finite. And we can incorporate uncertainty very easily. We have, a principled model with priors, and so basically uncertainty is propagated. And also it's possible to include information from covariates, for instance, from meteorology on the mixture weights. So we have done that, and we have looked at source attribution around Gatwick Airport, just to give you very quickly an example. And so where you see the star on the map is where the monitoring campaign was happening. And basically running this type of machine learning model, we ended up with these 9 sources, which you can see the profiles on the left plot, which, they're nice, they're kind of like well distributed. So yeah, sure, great. But then, what do they mean? So really we need to go from there to something which is interpretable. And looking at the time profile, this was a time series over 9 months, and also looking at the covariates which we included, which was wind, we could actually disentangle that, for instance, there was this massive source, 25% of the concentration was coming from, with the wind from the south, which is where Gatwick is, compared to our monitoring station. So that is sort of like the airport component. Then we found something with the wind coming from the north, which had a really commuting pattern, and on the north of our monitoring station there is London. So that was kind of like an urban component. We also found a few more. So basically it's, it's where we went from the source profiles to actually interpreting that, which is really, the important part. So I'm just going to leave you with some discussion points. The data-driven approaches are great because they give us lots of flexibility, but interpretability is super important, particularly when we then try to feed this to stakeholders, for instance. Using different methods may increase robustness of the results. So, just sort of like maybe an ensemble of methods would be the best approach. And then the main challenge is how we do this, how we link this with health. And there are lots of sort of like, thoughts I've put down, few thoughts I put down in terms of challenges. Uncertainty, propagation, confounders, for instance, and so on. And then finally, dissemination is really critical and is not trivial, and is really need to be focused on the target audience that we have in front. And I am going to finish with the references and where to contact me if you want. Thank you.
Thank you very much, Marta. That was great. I wonder if I could just follow up on one of your discussion points on the dose response. So do you think we'll ever be able to kind of attribute health effects to different sources and look at maybe potentially different toxicities of different...
I think that's the ambition and the challenge. This is where we are trying to get. So the first thing is obviously trying to get to the source, trying to understand what the source are, and then is linking these sources to health. And obviously there are all sorts of issues related to, what type of studies, what type of epidemiological studies you then run, if it's an individual level study, which, would allow you really to say something causal, or if it's most likely sort of like a time series, an ecological study, which, I think they're super important, would certainly, carefully done, would really allow us to say something on the level of toxicity of the sources.
Fantastic. And so on to Matt Fry from the UK Centre for Ecology and Hydrology. And Matt's going to give us his presentation on climate change, water and AI. Over to you, Matt.
Thanks very much, Gavin. So I'm going to give a very quick run through, talk about different aspects of hydrological data and where there are opportunities to improve our understanding and our ability to deal with climate change. So the hydrological impacts of climate change are amongst some of the most severe. Increased temperatures in the atmosphere driving increases in rainfall intensity leading to flooding, increased temperatures leading to greater levels of evaporation and snow melt and variability in rainfall patterns, potentially leading to drought in some areas. And it's very important to try to understand both the potential impacts from climate change, and also to understand how we can use our information that we have available to cope with that and to adapt to climate change. And the picture on the right here shows a recently released data set on changes in river flows across the UK based on the most recent climate change projections. And we need to harness this information to help improve our understanding of climate change. So firstly, we ask ourselves, are there impacts already occurring? And there's a huge amount of work underway in looking at various different approaches to understanding this question. There are attribution studies involving a lot of modelling statistics to try to identify whether some of the recent events we see in the news, flooding and drought events around the world, can be put down to climate change. And they've been quite successful in identifying that. For example, the recent terrible floods in Germany last year, where these studies have identified that they could be up to 9 times more likely based on due to climate change. The graph on the right there is looking at trends in river flow data across the UK, particularly in the annual maximum data, the sort of flood event data. And there we can see a mixed picture of increases and decreases in flooding over the last 30, 40 years. But it's worth understanding that when we look more closely and we look at trends over different periods of that data, we can get a different picture. But there's definitely evidence of an increase in flood intensities in some parts of the country. So what type of measures are needed in relation to hydrological risk and climate change? So here's a selection of some of the things that we need to look at. So firstly, it's understanding that risk, both in the short term for flood forecasting as we move forward into a changing climate, but also these long-term predictions, these climate change models, and understanding how they translate into impacts to the hydrology, to flooding and droughts. Improving our ability to make those predictions. A key part of it is around communication of that information, as we've heard already this morning. There's evidence that there's been a discussion around that terrible flooding in Germany last year, how better communication of the data that was available, the information on flood risk, may have helped to reduce some of the impacts. But there's also a need to communicate these potential future impacts to communities and to people making decisions on the ground. There's a need to think about adaptation, whether that's built infrastructure or changes to the natural environment that may have potential to reduce flooding and droughts. And that adaptation obviously needs a huge amount of investment. And to make those investment decisions, we need better data, we need better information, and we need increased levels of certainty about where the most effective adaptation measures can be made. It's not all about kind of adaptation and dealing with the hydrological impacts of climate change. There's potential for mitigation as well in relation to hydrology. For example, increasing water levels in wetlands. Recent studies have shown in peatlands that there's potential to increase the carbon uptake by the soils at the same time as improving the quality of habitats and providing a bit of resilience to biodiversity change. So where can AI and data science help? Here's a selection of some areas where there's a lot of potential. So producing, there's a whole range of new monitoring techniques in development. The slide on the left shows a sort of non-contact method for measuring river flows, just from a video, from a camera, increasingly from drones, and we're also looking at similar sort of video footage from space now. And you can track the velocity of the surface across the surface and use that to get remote and potentially quicker measures of the river flows in different places, potentially places that were hard to reach at the moment. The slide on the right shows a new study linked to the University of Oxford, where deployment of large numbers of these smaller satellites that don't have a huge onboard processing power or data transfer can run AI tools on the satellites in order to do things like mapping flooded areas from space. And the fact that you could do this on these small satellites with much better coverage could give us much more data for sort of disaster response. There's aspects where we can improve the data that we've got already. So the data, as we've seen earlier, the data that we have and the decisions we need to take based on that data makes that data incredibly important. We can improve the quality and availability of data that we have. The picture on the left shows our machine learning tools for quality control of data. As we potentially increase the number of sensors we have in the environment, handling that volume of data, particularly handling the quality of that data, means that we need to scale up our ability to quality assure that data with reduced amount of human input. So machine learning tools have got a big role to play there. On the right there, we're showing how there's a potential to use a huge diversity in the range of data sources on sort of urban surfaces, social media data, citizen science data, data on housing stocks and how they might be impacted by particular flood levels. And there's a role that's there for AI to bring that data together to produce kind of larger scale data sets. And there's work at lots of research underway, including at the University of Newcastle in this area. So improving our ability to predict, so both these short-term and long-term climate predictions, weather predictions, and how they feed through to hydrological models. And in particular here, how we can bring together these existing models, which are usually based around the physical processes in the system that can be quite slow to run, that sometimes be hard to bring these new sources of data together into. And we can bring those process models together with machine learning models to bring the benefit of both types of approaches. We need to make sure that those AI machine learning models are interpretable, that we can use them to explain why they've made those decisions, and improving the predictions from blending predictions from different systems, making sure that those climate and hydrological forecasts can feed into social economic models. And the final slide, there's a kind of concept called digital twins for the environment, which we're working on at the moment, which is considering this as a kind of framework for doing these things. So bringing together lots of the new sensor data and monitoring data that's out there and allowing it to have access to machine learning tools, merging machine learning and AI approaches with these process models, delivering both a real-time understanding of what's happening in the system, but also supporting modelling and scenario assessment for the future. But importantly, and I think this relates to some of the talks earlier, it's really opening up those model outputs to make them understandable, make them accessible to end users, and make them available to decision making for the future. So thanks very much.
Thanks, Matt. Fantastic. And some of the ideas there about using drones and to actually look at river flow automatically, I wondered, it all seems fantastic with a lot of potential, but how close are some of these things to reality? Are they still kind of the research stage, or are some of them close to kind of being rolled out?
There's a lot of work in across all of those different areas I mentioned already. There's a lot of machine learning for hydrological modelling underway. So there's huge potential to do some of those things kind of almost immediately. I think the exciting thing is this aspect of bringing process models and machine learning models together, and there's research underway there. And I think we need it's the stage to think about how we can kind of properly benchmark those processes, how we can make sure that those benefits from those types of modelling approaches are genuine, and then work out how we actually deliver those into operational tools. I think we're at that stage.
Well, thank you very much to our three panellists for their presentations. Now I'm going to turn to questions from the audience, which are appearing on my iPad in front of me. One of the ones I thought might be useful to kick off with, because it was mentioned in, I think, all three presentations, is communication. We're dealing with complex data, big data, lots of data from multiple sources, complex models. How do we best communicate that in an easy and understandable way to stakeholders, local councils, decision makers, and other bodies. And I wonder if we could start with Matt, whether you have any thoughts on how you take all that complexity and actually explain it to people in a way that they can use the information and make decisions.
That's a very important question, and there's a lot of work we've been doing work in that exactly that area. It's really important to understand that there are lots of different audiences that need this information. There will be experts who need the detail of that data. There will be decision makers who need a different level of detail, but they need the assurance of the quality of those outputs, but they also need to be translated right down to the simplest to the level that can be explained to people on the street, particularly thinking about the need for quite significant change to the way we live and investments from society into infrastructure. It's really important to make sure that people have that information available, and the types of tools we've seen already are really important for that. And we need to make sure that we can bring those systems together to make sure that we're delivering all of that detailed climate information, hydrological information into those tools in a simple way that people can understand.
Thanks. And maybe Marta, do you have any experiences? I'm assuming that you don't have any problem explaining Dirichlet priors to non-experts, but do you have any experience or thing you'd like to add?
Well, I think it's, as Matt was saying, it's very important to kind of like understand exactly who we are talking with. And I think, visualization, for instance, is a very important tool which can be, very helpful. And obviously there are really fancy, apps that you can kind of like have where people sort of like just click a button, the model runs, and so you get the very nice output. And that would be nice for a specific audience. I think we've seen it with the COVID pandemic, how scientists struggled sometimes to kind of like pass the message to, stakeholders. So I think it's kind of like a very clear message. And engagement from the beginning, if possible. I think, that would be my sort of like positive experience, engaging from the beginning with the stakeholders would allow to sort of like for them also to understand how difficult the process is, how complicated it is, and kind of like asking questions, changing the sort of like the perspective, and trying to give their input, and sort of like that would help, I think.
Thank you. And Emma, you've been involved with stakeholders, I believe, right from the very beginning, and obviously the potential effects of climate change are enormous. How did you kind of narrow that down to something they were interested in, and also that you could work with them?
I think the key, as Marta was saying, is that conversation at the beginning to understand what their questions are rather than start from where your questions are. And that does lead you to in a very different direction of travel in developing the project. But I think in terms of communication, I think one of the things that we've found with working with our stakeholders, and it's something that I think often as a researchers shy away from, is saying what are the implications of the data. So for many people, actually, that knowing what the data is and knowing what to do about it are two quite different challenges. And often local decision makers, certainly, who are taking some of this information, don't have the experience or background or confidence to make that leap from what the data says to what they should do about it. So there's a reluctance often to say to people, so therefore you need to do. But it is the so what question that is often the one that we need to answer, and then provide decision makers with that opportunity to drill down through the layers of evidence to understand where that recommendation may have come from. I think perhaps that would mean that there's a greater opportunity for decision makers to actually make use of this data and to make use of the information that we're finding.
Thank you. I'm not going to paraphrase a question that's come in, which is actually specifically, Emma, on the use of UK CP18 climate projections. And I think what the question was saying is that, are they good enough for kind of very localised effects, and how that would then feed through your models into impacts. But I'll generalise that question, and I think I hinted I might want to ask this anyway, into is the data available to do what you want? I mean, we hear that there's lots of sensoring, remote sensing satellites, climate projections, numerical models, enormous amounts of data. But is there any barriers to that data being available and actually being usable for what you're trying to achieve? So I wonder if we could start with Emma.
Yeah, I mean, I think that's one of the key challenges and why we're hoping that our latest association and collaboration with the Turing Institute and the DIME project will help us to take what are very complex climate models and do that interpretation. I'm not a data specialist myself, so it's not something that I have expertise and capability to do, but it is really very interesting talking to local decision makers about their lack of understanding about the local climate change that is coming, and therefore asking people to make decisions about climate change without any real concept of what the local challenges are going to be. But I do recognise that there are a whole host of challenges, and how do we use the data in such a way to get meaningful local climate models, and also what the conversation still needs to take place is how detailed do those climate models need to be in order to make them relevant and valid. At what scale do local decision makers need to work? How much change do they need to be aware of? What factors do they need to be able to take into account? I think that is a big piece of work that's still required. But certainly the models that come from the Met Office are great, but at the moment you need a PhD to interpret them, and that's what's not available at a local level.
And Marta, do you have all the data you need to answer all your questions?
Well, it's actually an interesting question, because on the source apportionment there is a limit, because they're quite expensive still to kind of like get all the components, while the ambition would be to be able to have a spatio-temporal model, so you have something quite localized. In reality, you have monitoring campaigns. So, I think in London there is one super site with loads of data, but it's one which serves, the entire of London. So really, it is kind of like it is a big challenge how you sort of like try and infer from this limited data to sort of like something which is a bit more generalizable. And I think it's still very much a challenge.
Matt?
So obviously the UK CP18, that sort of programme of providing consistent national projections is incredibly useful, and it gives a basis to build on, for example, those models of the modelled river flow, future river flow data that we've just been working on. But it's really important to allow the kind of propagation of the uncertainties from those climate models through to the kind of impacts to come through as well, and capturing that's quite a challenge. In terms of our ability to understand current changes and the way the climate change is currently affecting the hydrological system, it's really important to have those long-term sites and those sites that are unaffected by other types of change in that sort of monitoring record, to make sure that you're genuinely able to understand which changes come from climate variability over that timescale, rather than from land use change or urbanisation and those sorts of things.
We've got a question on scalability, which was for Matt originally, but I'll broaden it for Emma and Marta as well. And really, I don't know whether your river flows and things are in one specific area or river, but are there going to be challenges in kind of doing comprehensive coverage across the whole of the UK? Is there a need to do that? And if there is, what might be the barriers, either computational or other?
There's a lot of work going on at national scale across the UK, people working down at the sort of kilometre and finer scales. I think there's the other end of the scale. There's, in terms of understanding the processes in catchments and how changes to climate and other kind of adaptation measures might affect hydrology. It's very important for us to be able to monitor more at a higher resolution and smaller catchments, and really work with models alongside highly instrumented catchments to really understand the process that are going on at that scale, and then be able to scale those up to the national level. And that's the kind of thing we're looking at in the digital twin projects that I mentioned.
And Marta, your example at Gatwick, is that something that needs to be done eventually for the whole of the UK, or maybe globally? And I don't know computationally how hard or difficult it is to fit your Bayesian models, but is that something that might be a challenge? Or are there any other kind of barriers to getting comprehensive information?
Yeah, so there is the data challenge, which we touched upon before. There is obviously a computational challenge as well, because I think the model we just ran took 3 days. And if you kind of like start to build it up, and we haven't even included health, because I think it's even more important, I think, when you want to link in, to see if there is an effect, a health effect, it's probably, for particularly for pollution, but for temperature, for other stressors as well, it may be very local. So, it is quite crucial to go sort of like quite high resolution in space, which creates, a sort of like an additional barrier in terms of computational burden.
And Emma, I think in one of your slides you talked about nationalising the LCAT. Is that a simple task?
No, frankly. I mean, the main challenge that we're encountering at the moment, and I'd say we've still got a long way to go in our journey with our stakeholders, is that getting the local climate models that are meaningful and have the necessary corrections. So what we are looking at is, do we need to take sort of a geographically local but diverse across the UK, so sort of example sites that might provide us with that as a starting point. But I think there's, as a non-technical person, this information is there. What we haven't got is that intermediary point that makes it accessible, and that's the challenge, I think, with a lot of the climate situation, is you've got non-specialists having to work with very specialist data, and how do we make that? How do we address that challenge using whatever models of machine learning, AI, whatever it is that we need to apply to make the information accessible?
Thank you. And another question originally for Matt, your presentation, obviously a good source of inquiries, was on, you briefly mentioned citizen science. And maybe we might think more broadly about engaging the public. We've talked about stakeholders and the policymakers. Do you have any experience on kind of using data from citizen science? And are there any specific challenges integrating that with data from kind of monitoring networks and kind of research studies? And then maybe more broadly as the second point, how do you think we can engage the public in what really are quite complex issues of climate change itself, but also the use of AI, which for many will be seen as a black box?
I think citizen science has got a huge benefit across all those areas, both potential to provide more data, but also that aspect of engaging people in that process. And we talked before about people understanding the climate situation. And there are lots of local catchment rivers groups who are doing a great job at engaging with local people to improve, their primary interest is improving just the local state of their environment. But as they do that and they get involved, they're understanding more about these issues, understanding more about the pressures, and understanding more about what they can do about it. And that really helps to kind of get that message out there, and getting the public heavily engaged in that is really important. And there is a lot of great work going on in that citizen science area. It's really being, in the sense of hydrology and river water quality in particular, it's really being ramped up and seen as a tool to both to increase that engagement, but also to provide sources of data and evidence for that. The issues come from trying to do that in a way that make sure that data is done to a certain level of quality, that you can understand the quality of that data that comes through, making sure that the measurements are in the places that are most useful, rather than just done where it happens to be convenient or happens to be a nice place for people to go and help do that monitoring. And there's great works, for example, by the Rivers Trust, which are trying to standardise the citizen science methods that are used in rivers, to provide advice to those catchment groups, and looking to help to integrate that data back together, so that you have a kind of, rather than lots of local pools of data, you're building up a national pool of that citizen science data that can be fed in alongside the kind of more regulatory monitoring to inform those informed decisions. And it's potentially quite promising in a lot of areas, but I guess the first step is understanding how much that additional data can add power to the analysis and the understanding of the situation.
And Marta, what about using citizen science in air quality and health studies? And we do have a specific question from the audience about whether you could incorporate potentially low-cost air quality sensors into health and epidemiological models.
I think it's a great question, and it is a possibility. I think people have started looking into that. It is obviously the drawback, as kind of like Matt was saying, is the quality of the data, understanding are the data up to the task, and you obviously need lots of calibration. You would you, in a way, you would need sort of like an additional complexity maybe in the model to allow for this data integration where you have, you know, less accurate and more accurate data and kind of like, but you know, it improves the power immensely and it improves the engagement. Again, it's sort of like, you know, it's really dealing, you know, talking with the public from the beginning, and it's much easier then to pass the message, I think, you know, at the end. Like for instance on the air pollution sources, one thing that is coming out is the biomass burning and all the stove, you know, sort of like, which are very popular, apparently being really bad. And you know, I think if you can engage the people from the beginning, it's much easier then to keep this conversation alive.
And Emma, do you have experience of public engagement when it comes to?
We haven't so much with LCAT so far, but it is something that we've been looking at, and we're particularly keen to do it with qualitative data, so looking at how we can integrate people's personal experiences of climate events and sort of responses into LCAT to demonstrate and give confidence to people around the sort of the inclusion, through the inclusion of things like case studies, both of what people have done, but also how people have experienced sort of severe climate effects to demonstrate the value and the necessity of action. Because I think that's something, again, that in a world where we have got so many different crises that local decision makers are trying to deal with, actually making sure that there is an understanding of the long-term requirement for change, and that these decisions can't be left until there aren't any other crises to deal with, and that we start to look at that more urgently.
One of the points, and again a question from the audience that I think was in the slides of at least two of you, maybe three, is the idea of kind of uncertainty. And if you have different climate projection models, that there might be different projections, different scenarios. If we've got measurements from monitoring sites for air quality and also remote sensing satellites and models, also how do you allocate those exposures to different people? So uncertainty is a technically complex issue, but I wonder, you may have some thoughts on that. But also, how do we go about explaining the uncertainty and kind of informing people how uncertainty should feed into their decision-making processes? And I wonder if we could start with Matt.
Yes, as I said before, that propagation of that uncertainty that we know is there in the climate models through, in my case, the hydrological models is very important, making sure that uncertainty information is just captured alongside the data that's available to people, that they're not just given single sources of data, that uncertainty information is there, it's kind of upfront and very clear about where those uncertainties come from, is very important. And then, as I've said, it could be making sure that that's data, the uncertainty information is available to feed through to other decision-making tools or other models, or, as Marta mentioned earlier, making sure that it's able to be visualised, that people can actually see what that means in relation to the projected change, that exactly what those levels of uncertainty may be.
Marta, any thoughts on uncertainty?
Yeah, I mean, I really like uncertainty. Very like, you know, it's something I deal with every day. But basically, linking to what Matt was saying, I would say visualization is quite a good tool to try and communicate uncertainty. I'm finding, in a way, it's easier to communicate uncertainty to the general public than to the decision makers, because the decision makers have to make decisions. They want to know, is this or that? And, you know, sort of like feeding in the uncertainty there is more challenging, and I think it needs to be done in a way where, you know, they need to they understand that is important, but it's kind of like what you do with that at their level, which is, you know, harder to sort of like to deal with. But yes, I think it's absolutely important, and it is important to propagate it. What we usually, unfortunately, still do in the air pollution realm is, apart from Nugamin obviously, is to sort of like have these models which are very complex on the air pollution side, then we take the average and then we just do the average, we put the average in epidemiological models. So we don't really put through all the uncertainty, which obviously it's something, you know, it needs to change, because it is important, and you know, it would change the results. So.
Emma?
I would agree with Marta. I think for decision makers, uncertainty is very difficult to handle, particularly if they're being asked to make decisions in areas that they don't feel confident or don't have a background or an understanding that is deep enough to be able to explore where that uncertainty comes from. I don't know what the answer is. I think that part of the responsibility, I guess, of those people who do understand that uncertainty is how do you communicate that in such a way that it doesn't become a barrier to action. Because often I think when you're faced as a decision maker working in an area that you're not confident in, you get faced with something that says, well, it might be, but then it might not be. What do you do with that information? How do you make a decision? So I think there's a real necessity for those that do understand it to really work on how do you communicate it in such a way that it doesn't stop a decision being made. Because I think that's one of the big challenges that exists for climate change at the moment is the uncertainty about the modelling and the uncertainty about has actually been the barrier to action.
And another question actually generated by Matt's presentation, which is, what's the best way for me to find out if my own house is likely to be flooded due to climate change? And just to broaden that out a bit, I think we might maybe discuss the role for AI, data science in almost personalised environmental risk. So does my house flood? What's my exposure to air pollution? And could I change the way I go to work or school and reduce it? And in terms of kind of my heat exposure, is there something I can do about it? So can increased access to data and sophisticated AI methods help us? And I'll start then, Matt, with the original question. How likely is my house to flood? Of course you don't know.
I don't know where you live. That is a very difficult question, both on the certainty of that information and the scale of the information that you probably need in order to answer that. I think there's probably a role here where it's not down to researchers to communicate that information, but it's about making that data available to different groups that can translate that into that understanding on the ground. That will inevitably be done through insurance companies, for example. You'll inevitably find out in your insurance premium as whether there's any certainty in the likelihood of being flooded in the future. And authorities like the Environment Agency are taking that information on board and understanding how and where there is certainty in that information and how to communicate that to people. I'd say, yeah, if that doesn't sound like a cop-out, it shouldn't be down to researchers to tell people where people's houses are likely to flood.
Okay, thanks. And Marta, you mentioned taking averages across areas and assigning them to individuals. Do you think there will ever be a day that we'll have the data and the methods we need to kind of assign personal exposures to air pollution?
I think, going back to the low-cost sensor, if in an ideal world, if you can kind of like calibrate this, if they're, either if they're good quality or if you can sort of like calibrate it in a, machine learning AI model, and then everybody has these sensors, you could kind of like find out, at this peak time, this street is really polluted, just take this other route. So you can really try and change the behavior. I think it's still quite a long way away, but why not? I think, that would be really, really, really good for a grant.
And Emma, thinking about inequalities again in terms of exposure to heat, if it's going to get hot in urban areas, is that something that we can estimate now, or is that something that will need research and going forward?
I mean, that's the project we're doing through DIME and the Turing Institute is looking at exactly that, and looking at how different populations or different groups will experience heat and how heat exposure is impacted by behaviour, whether you spend a lot of time outside, whether you're inside, the different types of construction that your home might be built of, and how that could influence your ability to manage heat, high levels of heat. So I think that it's a bit like Marta said, there's more that can be done, the future is there, but yes, the potential exists to look at that. Whether you'll ever be able to personalise your climate change experience, I doubt. I'm not sure what value it would add, frankly, but I think understanding the general sense of what the consequences are of, say, heat and on human behaviour, we already know that heat can impact on people, can become more aggressive. It can have an effect on our law enforcement. It will have an effect on how many people end up in A&E with heat exposure because they've spent too long on a Cornish beach, and those sorts of things. So it will have very dramatic effects at an individual level, but whether you'll be able to measure it quite like that, I'm less convinced.
Well, thinking to the future as well, I wonder if we could just turn to what do we think the main kind of opportunities might be going forward. We've seen from your presentation the kind of discussion going forward slides, but I wonder if you could sum up what you think the opportunities might be in your field, and then maybe briefly touch on some of the challenges, whether that means access to more data, more low-cost sensors to fill in data spatially and temporally, or whether it requires new monitoring networks, or whether it's a computational issue, or maybe there just needs methods development because we've got all the data we need, we just don't know how to integrate it. So I think we'll start with Matt, if that's okay.
So I touched on some of those potential opportunities in future. The ones that I'm particularly interested in are the potential to deliver new monitoring data through to improve our kind of understanding on the ground, to improve our understanding of those processes. And there's definitely a role for AI and machine learning in both improving the quality, sometimes in actually processing that monitoring data could be from a sort of different non-conventional kind of sources of data, but also in improving the quality of that data and understanding how we integrate it into those models. I think that's my particular area of interest.
Marta?
I think in air pollution, the data are there. Basically, we have GPS. We obviously have the monitoring network. We have satellites. We have GPS. We have all this, which can be combined, and where there is the scope for AI, definitely AI, machine learning. It's a computational. The computational burden is quite intense. And it is, I think there is still the need for some, modeling approach to combine all this in a principled way, maybe linking the health as well, and accounting for all the uncertainties. So I think we need to go in that direction.
Yeah.
I'd be interested to see whether AI and machine learning can help us interpret the data in a way that is understandable to your average user rather than your specialist, and looking very much at the potential of being able to adapt systems to the individual's background and experience to make that information then much more accessible. I think that's where I'd like to see work, but it's not my area. I'm definitely a beneficiary of technology rather than a user.
And I wonder if we could just touch on a point that Matt said, which is about basically data quality and data assurance. Of course, having lots and lots of data is great, and sophisticated, complex models great, but if that data isn't quite what we think it is, if it's got unintended biases, and we've talked about uncertainties. I wonder about whether we could just expand a little on your automatic, using machine learning, for example, to, I don't know whether you kind of triage data and you actually go as far to putting some aside and not using it, but I wondered if you had any thoughts on where that might go.
Yeah, like I said, I think with increasing amounts of sensor data out there in particular, that it's the challenge of managing that is increasing, that is potentially very time consuming. So any efforts towards automating those processes. And I think, but there's a risk there that you're using tools that just have learned from other data, or learned from the relationships between the data that you're monitoring and other sensors that could if you're just using that automatically, there's a risk to throwing things out that you shouldn't, or you're just kind of driving towards similarities in the data rather than necessarily identifying differences. So it's potentially more about using it as a way to automatically flag that data up, make sure that it's a way to bring forward the data that needs more scrutiny, to make sure there's still human input to that. And the other challenge, I think, is making sure that we've got the pipelines of data, that we are properly integrating those sensor networks, that it's not 1,000 different networks operated by different people, that we're working towards standards and sharing of that data so that those could be brought together as a kind of sort of network of networks to really give the kind of contextual information to make those decisions about the data that we're producing.
Thanks. And Marta, any thoughts on data quality and the effects it might have?
Yeah, I mean, data quality obviously is very important. I think it's, as I said, I mean, there are ways of sort of like calibrate, at least, the air pollution word, calibrate data and sort of like trying to account for uncertainties and biases. Obviously, they are quite, complex and add to the complexity of the model. So, but yeah, they will give, great advantages, I think. So it's certainly, it's just recognizing that the data are different qualities and do something about it, trying.
And Emma, when you've dealt with stakeholders, is this something that's a concern to people, that they might be making decisions on data that is biased or maybe is from a different area than they're particularly interested in? I wondered what the kind of perceptions of data quality, data assurance and its effects might be.
I think there's a sort of a sense of trust to some extent of where data comes from, and so if it comes from an organisation that is reputable, that many of those factors will have been considered. But I think one of the factors that in thinking about data is that sort of unintended bias that often exists within data, and how that then extrapolates through the various cleaning processes that, as you said, Matt, were kind of a part of it. And I think one of the areas that's of particular interest is that sort of the sense of how do communities that are often the most vulnerable but are often the most excluded from studies, and how is the consequences for them represented in the data when often they're not part of the process that's generated that data. So thinking very carefully about inequality and vulnerability and unintended bias is really important.
Yes, absolutely. Well, we've come to the end of our time. Thank you very much to Emma, Marta and Matt for a fascinating and very informative discussion, and plenty of ideas there for how AI data science might help us tackle climate change and the effects of environmental change, and also the wider issues of how we can use it responsibly and explainably in society. So with that, I'll say thank you again, and thank everybody who's been watching.